Hi folks, now we're on the last section of the Earth and Moon system, and we're going to be talking about the Moon now. And the topics we're going to be concentrating on are the basic characteristics. Primarily we're going to be concentrating on where it came from and how did it form. And as an ending, I want to show you an example of the connection, truly a connection between cheese and the Moon. All right, so what are some basic characteristics? Well, when you look at it, what you see are craters and seas. When you look at it with the naked eye, it looks like a billiard ball, basically, that looks at a little discoloration in some places rather than others. But when you look at it with a telescope, even a pair of binoculars, you're going to see craters and smooth areas that we call seas. The orbit is such that it takes about a second and a quarter for transmissions to occur between the Earth and the Moon. You can see the effect of that when you take a look at YouTube and the videos that NASA took of the astronauts in there, and how the conversations sort of seem to, you have to wait for a reply. The average distance between the Earth and the Earth and the Moon is 380 kilometers, or 380,000 kilometers, but it does range from 405 to 365, so there's a bit of a change there, about 10%. Something quite a bit more than what we see with the Earth around the Sun, which is on the order of about 5%. There's a bit of a difference between the solar and the sidereal rotation period of about a couple of days, and there is a rather significant, well, not maybe 5 degrees isn't a big inclination, but the Moon is different. It doesn't really lie along the ecliptic, and for that reason we don't get a lunar eclipse and a solar eclipse every month. We only get it 2 times a year. So for a total of 4 times per year will we see an eclipse of any type. The Moon is about a quarter the size of the Earth. We saw that a couple of weeks back, and how the Greeks actually measured such a beastie. But on the other hand, the Moon is made up of a different material, and so the mass of the Moon is quite different than the Earth. And we can see that, and we saw that before when we watched the YouTube video of the Apollo astronauts dropping a feather and a hammer on, on the Moon, and we saw how slowly those objects hit the ground, so to speak. From this information, we can find out that the density of the Moon is about half that of Earth. There are atmospheric traces, and as you may know, water ice has been found in craters in the northern and southern reaches. The temperature ranges from a low of 93 Kelvin to a high of 403 degrees Kelvin, basically because of the atmosphere, but when we're in the night side, we are actually looking into deep space. Very interesting effect here. The albedo is only 6%, meaning that only 6% of the light is reflected. The rest of it is absorbed, which may be kind of surprising because the Moon creates shadows at night for us. So quite a lot of light is hitting the Moon and being reflected back to the Earth, even though the amount that's being reflected is small. But if you have a big intensity hitting the Moon, then a small amount of a big intensity could be quite a lot. So that's why we get shadows, moon shadows, if you will. When we look at the Moon, we see craters everywhere, and we see all sorts of different characteristics of craters. As exemplified by this middle picture, we can create regions where the center region is higher than the middle portion, as exemplified by this crater here. We have an interior portion that's raised up between then around the edges here. We can see splashes, ejection splashes. We see that frequently on the moon as well. Examples of on the Earth, meteor crater in Arizona and the Tycho crater on the moon, very representative of each other. Impact cratering, similar to Earth. A lot of it occurred right after the solar wind pushed everything away, and we had large objects hitting medium-sized objects in the Earth. I don't know if we can get this guy to play. I guess not. The Maria are basically lava fields, and we'll show how that's been created. They occurred after most of the craters were formed, and we can see these riles on the lava beds, basically where the lava cooled and various pieces of it broke apart from each other. And this is how we believe the Maria were created. So we had a big impact. The impact created fissures in the rock very deeply, and the molten lava then came through the fissures and filled in the spaces of the crater and then flowed out onto the surface, basically refreshing the surface. Here's another example. We can see craters on top. So these craters are newer than these craters, well, than the Maria, and this is newer land, if you will, than outside here. Some areas are more heavily cratered than others, and basically we know the reason why, because the younger regions were flooded by lava and covered up a lot of the craters. The near side is different than the far side. Basically, the far side has lots of craters. The difference, as illustrated here, is basically the Earth is in between. So the Earth protects the near side from the craters. So here's the near side, and we have lots of Maria from the big asteroids that hit the moon. The Earth was not able to stop them, and the big asteroids or comets hit the moon, dove down deep, and the lava came up through the fissures and covered the regions. On the other side, any little asteroid can come and hit the surface, and that's why we have many more craters on the far side than on the near side. In a similar sort of fashion, the moon protects the Earth from getting hit by asteroids as well. But here's an example here of a nice set of rays coming out of this crater. There is a material on the surface of the moon called regolith, and it's also on other planetary formations. The regolith is created by meteorites hitting the surface and then causing a cloud of material to get thrown up into above the moon, and then it settles back. So it's basically, if you will, a bunch of dust particles and stuff like that periodically gets thrown up into space and then comes back down. And so you're basically walking around on a layer of dust, and that dust can be quite deep in places. Here's some pictures of materials that were picked up by the Apollo astronauts and brought back to Earth. We were able, we as humans were able to understand a lot about the formation of the Earth and the solar system from these rocks from the moon. The radioactivity that we've determined and that we've measured on these rocks tell us the age and the history of the sun actually impacting upon the moon. I mean, the impact being solar wind and light and things like that. Now, the moon is green cheese. It's kind of interesting. Here's an example of velocity of sound for different types of cheese, and for lunar rocks and for terrestrial rocks. And what's interesting is if somebody says that the moon is made out of green cheese, well, you can say, well, it has similar properties. The properties are quite different than terrestrial rocks. So kind of a little funny. As I think this chart is a little bit old, we have observed water ice in polar craters rather than just saying there's a possibility. The same is also true for Mercury as well. Now we're going to talk about lunar formation. These are the major theories associated with it. Fission hypothesis, condensation, capture, large impact hypothesis. And it's this last one that we currently believe to be the best explanation about why the moon is there. So as you can see here, fission is basically the moon broke away from a rapidly spinning Earth. And basically the idea that gave rise to that, or the evidence if you wanted to say that, is you can fit the moon inside the Pacific Ocean. The ocean is deep, and so, people once thought, okay, well, it fits there, so that's where it came from. Another hypothesis is basically the moon and the Earth formed from the same cloud of material. In this particular case, you would consider the orbit of the moon around the Earth, and if the moon and the Earth were created from the same material, then the angular momentum of this system would be such that the moon would would be just sitting above the Earth's axis. I mean, not the Earth's axis, but the equator. And what we see is the moon goes around pretty close to the ecliptic. 5% off, but it isn't 23. And so the moon goes around basically controlled by what's going on with the sun. The capture hypothesis is sort of, out there as well, but capture hypothesis sort of is, we would suspect something much smaller to be grabbed by the Earth, something like an asteroid in size. Okay, so here are some computer simulations showing you the collision between some massive object, the size of Mars is considered, and then we come over to here, it gets spilled out, and here we have spilling out some more until finally we have a coalescence of material that formed the moon, and the rest of it falls back into the Earth. Okay, the nice thing about this collision hypothesis is we not only get the moon, but we get the tilt of the Earth as well. So 23.5 degrees is quite a bit different than 0, which is what we see with Jupiter and Saturn, and Neptune for that reason, on the same token. But the idea here is it's quite a bit different. But if we have an impactor that's coming off axis a little bit, doesn't graze it, but hits it off onto the side, then we can create something with a large angular momentum, as well as a tilt. And then we get the moon as well. Here's another picture showing, the knowledge that we've gained from radioactive dating of rocks that are coming from the moon. We don't know everything about what's going on, but we know quite a bit of material about what's going on. Okay, and we find out, for example, that the moon and the Earth are made up of really the same stuff. Okay, what I want to show you now is some ideas, some simulations showing 3 of these models, and this is the pictures associated with these guys, and I think the next chart will show us each one of these, hopefully. So here's the first one. So this is the standard model. It's interesting. I didn't know it hit twice. Okay, here we go with the fast spinning model. And sub-Earth model. It's kind of fun what you can do with these simulations. Okay, thank you very much.